All right, senior math, welcome back. Last Friday we dealt with binomial. Today we are going to be working with Poisson distribution. Poisson distribution is very similar to binomial distribution. The scenario that we use is just a little bit different. But let's do a quick review over binomial distribution. So biology class wants to see how many of the students in the class are tasters, which a taster is like someone who can like taste sour and bitter foods really well. It has been established that 70% of Americans have the taster gene. If there are 20 students in the class, find the different probabilities. So let's find the probability that exactly 15 students are tasters. So let's first figure out our information that we needed for binomial distribution. So the three pieces of information we needed was we needed what n was, we needed to know what p was, and we had to figure out what our k was for the different situations. So in the first part, we know that it's 70% of people have the taster gene. So that's going to be our probability. So our probability is going to be 0.70, 70%. There are 20 kids in the class who are being tested. So we're having n be 20. And then for our question, we're looking for exactly 15 students. So our probability of x equaling 15. Now that 15 is going to be my k for my problem. So what I had to do here is I had to pull up my chart, pull up my little chart, and then I had to look for n equals 20, p equals 0.7, and then I would have to go all the way down to k of 15. And from there, I just had to write down the number. So I got k of 15 equaling 0.179, and that was my solution. Now, what was the probability that at least 17 of the students are tasters? So when we get these at least, it becomes a little bit harder, or at least, or at most. When it was exactly, we just had to write down the number. When it was at least, it was a little bit harder. So this is saying, what's the probability that x equals 17? Now, this is only changing my k. My p and my n are staying the same. So I still look in that same part of my table. But this isn't equals. This is at least. So at least means the minimum number can be 17. So x needs to be greater than or equal to, because I can't be lower than 17. I can be 17, but that's the lowest possibility I can go. I have to be bigger than 17. So we have to think, what numbers are bigger than 17? Well, numbers that are bigger than 17 are numbers that are greater than or equal to 17 from the numbers 0 through 20 is going to be 17, 18, 19, 20. So those are our four possibilities. So we're going to do probability of x equaling 17 plus the probability of x equaling 18 plus the probability of x equaling 19, and then plus the probability of x equaling 20. So we have to add all three of those together, or all four of those together. And whenever all four of those add together, that would be our probability. So we should get 0.072 plus 0.2028 plus 0.007 plus 0.001. So adding all those together, we get 0.108. So roughly about, there's a 10 to 11% chance that at least 17 kids in the class would have this taster gene. And we had a 17 to 18, we had about an 18% chance that 15 kids in the class would have our taster gene. So that was our binomial distribution. Once again, binomial distribution only worked when it was like odd, or like you had either success or either failure. There was only two options. You had this or this occur. Poisson distribution is a little bit different. So for Poisson distribution, it's another probability distribution that can model different scenarios and is very easy to calculate the Poisson distribution. We're going to calculate pretty much the exact same way. We're going to use a table. I will hopefully print out these tables for you so you can have access to that. This distribution is used to represent the probability of a number of occurrences of a specific event in a given unit of time or space. So we're looking, what's the probability of something happening in some amount of time if we have a given average? So here's some examples. The number of calls received during a given period of time, the number of bacteria per a small volume of fluid, the number of customers' arrivals at a checkout counter during a given minute, the number of machines that break down during a given day, the number of traffic accidents that occur at a given intersection at a given time. So it's always, you have to have some sort of average to start with these. And then we can use that average and say, on this given day, what's the likelihood of this number of things happening? And we can calculate that using Poisson distribution. So once again, we have a funky formula for calculating Poisson distribution. This Greek letter that looks like a U with a tail, that's the Greek letter mu. That's a Greek letter mu. This represents average. When we talked about mean, median, and mode, we would use mu to represent the average of a data set. So anytime we're talking about mu, it's talking about the average, and that's an important thing for Poisson distribution. K, once again, K is the number we're looking for. So if we're asking what's the probability of having 18 car crashes on a given intersection on a given day, K would be 18. And then E is a funky number that you probably learned in Algebra 2. It's like 2.718 roughly. It just represents a number. Now, we don't want to use this funky formula because it's all different types of things. But once again, K represents the number of occurrences that might occur that we're looking for. U represents the average of expected events. So we're gonna use our chart because the chart is so much easier than this formula. So don't worry about this formula because it's gross. So we have a distribution chart to use as well, and it works almost pretty much exactly the same as a binomial distribution. The only difference is you only need to know two things. You need to know where is the average, mu, and what is the desired number of occurrences, which is k. Now, unfortunately, the chart that I found, the chart that I have for you, for whatever reason, has different variables. Instead of using mu, they use something called lambda, which looks like this, I don't know, like a weird stick figure that's like leaning to the side. So they use this instead, and I think they use x instead of k. But once again, they represent the exact same thing. Here I can just show you. So this is your Poisson distribution chart. So the average are these numbers at the top. So these are your averages. So if your average is 1, you would look in this row to the side. If your average is 1.5, you would look in this row. If your average is 2, we would look in this row. If your average was, scroll down a little bit. If your average was 4.8, we would look in this row. Now, K is going to be the number off the side. So if I'm looking for 8 and my average is 4.5, I would just use this number right here, and I can write that number down. It's still going to work like Poisson distribution, or still going to work like binomial distribution. The averages go all the way up to 10, I believe. Yeah, so the averages go all the way up to 10, and then it randomly has 20 down here as well, if we ever would need 20. But it should be for your averages should be less than 10 for most of the time. But that is our Poisson distribution chart. We'll look at that in a moment more in depthly. So the average number, so let's say the average number of traffic accidents on a certain intersection of the highway is 2 per week. Find the probability of no accidents occurring on this section of the highway during a 1-week period. So the average number of accidents is 2 per week. So on average, I have 2 accidents per week. I want to find what is the probability that no accidents are going to occur on just a random given week. So this is a Poisson distribution because we have an average. Our average, like we said, was 2. We're looking for what is the probability of x equaling, if no accidents, we're looking for probability of x equaling 0. So all I need to do, go to my chart, look for 2. So 2 is my average. And then I know x equals 0. I just have to look at 0, which is my first one, which is 0.1353. Try to make this a little bit bigger. It's a little bit better. 0.1353. So my probability is going to be 0.1353. I just have to write that number down. Once again, anytime we're looking for exactly a certain number, x equals, we just write down the probability. All right, find the probability of at most 3 accidents on this section of the highway during 1 week. So what's the probability that at most 3 accidents? Let's think, what does at most mean? At most means I cannot exceed. So I have to be less than or equal to. So probability of x is less than or equal to 3. Well, what numbers are less than or equal to 3? Because once again, just like with our binomial distribution, I just can't write down the number 3 or whatever my probability for 3 is, I have to think of all the numbers that are less than 3. Well, numbers that are less than 3 is x equals 0 plus x equals 1 plus x equal, or probability of, sorry, I'm messing up my writing, plus probability of x equaling 2 plus probability of x equaling 3. These are all numbers that are less than 3. So we can add these numbers together. And so we would look at, here's my 0, here's my 1, here's my 2, here's my 3. So I would take these 4 numbers here in this last row here. I would take these 4 numbers and I would add them together. So for us, that would be 0.1353 plus 0.2707 plus another 2707. Sometimes the probabilities turn out to be the same. Plus 0.1804. If we add all of these together, we get 0.8571. So the probability of there being at most 0 accidents is about 86%. At most 3 accidents. Sorry. Yeah, that's pretty much your Poisson distribution once again. Very similar to binomial distribution. We're just using that chart almost exactly the same. So suppose a life insurance company insures that the lives of 5,000 men on average have 42. If the actual study shows that on average 5 out of 5,000 42-year-old men will die in a given year, find the probability that the company will have to pay 4 claims during the given year. All right, so we have an average of 5. So we're looking for, so if mu is 5, we said what is the probability that in a given year the insurance company has to pay 4 claims. So 4 42-year-old men will die that year that are insured by them. So we're looking for the probability of x equaling 4. So once again, I know my average. I know my average is 5. My chart's going to come up. So I need to go down to 5. So scrolling down, 5 is right here. I'm looking for 4. So 4, if I go all the way over, is going to give me 0.1755. So if it's probability of, come on. If it's probability of x equaling 4, it's just 0.1755 because it's exact. Anytime it's exact, I just write that number down and I'm done. All right, last question. All right, a manufacturer of a power lawnmowers buys 1 horsepower 2-cycle engines in batches of thousands from the supplier. She then equips each of the lawnmowers with one of these engines. History shows that the probability of any one engine from that supplier proving unsatisfactory is 0.001. In a shipment of 1,000 engines, what is the probability that none is defective? Now, this question is a little bit harder because if we look at the information here, we're looking for the probability that none are defective, which means x equals 0. There's no defective engines. But the thing is, they didn't give us an average. They didn't tell us an average. They told us we have 1,000 lawnmowers and that the probability of one being defective is 0.01. So if we think about it, they gave us a number of lawnmowers and they gave us a probability of it being defective, but they didn't give us an average. But if we think about this, we can calculate what the correct average should be. Given a probability and given a number, we can calculate the expected or the experimental probability of our number of lawnmowers that should be defective. So if we multiply our number by the probability, this will give us our average. So we multiply our number of lawnmowers that we have times the probability of being defective, that should give us our probability, which in our case would be 1,000 times 0.001 is going to equal our mean, which for us is just 1. So our mean in this case is 1. So anytime they don't give you the mean, anytime they don't give you that average, if they give you the number and the probability of it occurring, we multiply those two together and that gives us our average. So we have a mean of 1 and we're looking for the probability of x equaling 0. So we're going to go up to 1, which is right here on my right-hand side. Probability x equaling 0 is going to be 0.3679. Equals 0.3679. Awesome. Very last question that we're going to do. What is the probability of at least 2 are defective? So probability that at least means the minimum number is going to be 2. So probability, that means x is greater than or equal to 2, because at least 2 is 2, 3, 4, 5, 6, all the way up to however many numbers. So probability of at least x equaling 2. So normally what I have to do is I would have to add all the numbers that are greater than or equal to 2. So 2, 3, 4, 5, 6, 7, 8, 9, on and on and on. But the thing is, it's much easier, rather than to think just like with binomial distribution, it's much easier for us to think in the opposite. So rather than solve for this probability, which I will have to add a lot of numbers together, I'm going to do the complement of the event, which is 1 minus the opposite of it occurring. So the probability of x being less than 2. Well, what numbers are less than 2? This would be, my numbers that are less than 2 is going to be 1 minus, because that 1 minus is from before. Numbers that are less than 2 is probability of x equaling 0. Probability of x equaling 1. And then we don't include 2 because we're not equal to 2. So if I add probability of x equaling 0 and probability of x equaling 1 together, I can then subtract that from 1, and that would be the exact same thing of finding my numbers greater than 2. So I need to find what is x equals 0, x equals 1. So I already know what x equals 0. That's my 0.3679. And then x equals 1 is actually also 0.3679, because once again, sometimes in Poisson distribution, we get the same answer. So this is 1 minus 0.3679, and I need to add these together first, plus 0.3679. So always add them together before subtracting them from 1. And we get 1 minus 0.7358 when they're added together. And then we can subtract that, and we get our answer should be, come on, get rid of that. Move. 0.2624 is our solution. And that would be our probability of x equaling greater than 2. So once again, if you have to add a lot of things together, see if doing the complement, the opposite of the event, is easier. See if switching it around is easier. Doing 1 minus that possibility of occurring, and see if that is easier for you to work with. So that is our Poisson distribution. Once again, it's very, very similar to binomial distribution. So if you're good with binomial distribution from last week, Poisson distribution shouldn't be too difficult either. Let me know if you have any questions. Other than that, we will stop it there.